Hey everyone, Mr. Fransky here. Today we're going to talk about Euler's method, and the way you pronounce this is Euler, kind of like Euler, O-I-L-E-R, right? Looks like Euler, but Euler was a super smart mathematician, did a lot of great things for math and calculus, and so there's this method that's named after him. It's an approximation method, so kind of like using rectangles or using linearization. In fact, this is a lot like linearization. And it kind of goes along with the idea of slope fields, where you don't have to know the solution to a differential equation to be able to know something about the solution function. So today we're going to be able to use Euler's method to approximate function values of a differential equation. So let's see what's going on. So vocabulary: Euler's method, linearization, differential equation, and over-under estimate. These are really important things. So how Euler's method works. So we have some differential equation. dy dx is equal to something. Okay, so you can make a slope field out of that, right? So you can make a slope field. You can like what different slopes are, different places, whatever is going on. I don't know. I'm not sure. Okay, and you can kind of get an idea of what a solution curves look like, right? So it's like, let's say you know the solution through your particular point is going to look something like, I don't know, like this. Okay, all right, but you don't know exactly what it is. And let's say that you know it goes through a certain point. Let's say that point, we call it our starting point. Let's say it's like, I don't know, it looks like I graphed it about 2, 1. Okay. So that is the initial condition. Initial condition. Looks really bad. Initial condition. But that's the only point that you know it goes through. Okay, so that's the initial condition. So then the question is, well, using that point, could I like find out what, so let's say the solution curve is f of x. Could I find out like what f of 3 is? Well, not exactly, right? Unless I can solve the differential equation, I can't exactly find out what f of 3 is. But using the differential equation, I could say, well, what if we used a line at that point, right? What if we used a line at that point to approximate f of 3? That's linearization, right? If we used a line, then we could get the line. And the way that a close approximation to the point. And the way I drew it here, it looks like that would be a slight underestimate, right? If we used a line, it's because the curve is concave up, the tangent line lies underneath. It'd be a slight underestimate. And so what Euler's method is basically a way to say, well, what if we did like linearization a bunch of times? So let's zoom in on that part right there. Okay, so let's say this is our curve. Let's say this is 2, 1. And we want to know what f of 3 is. Let's say 3 is over here. So instead of just doing linearization, where that just would be using a single tangent line to say, well, f of 3 is approximately this value. And to do that, all you need is a point, which we have, and a slope, which you can get from the derivative. Instead of doing that, what you do is say, let's split it up a little bit. So let's say you split it into 2 pieces. So here we have 2.5, here's 2. So let's approximate 2.5 using that tangent line. So that's going to find the point right here. And now, instead of going all the way out to 3, we're going to use a different tangent line. Okay, so I'm going to kind of make this smarter. I'm just going to go right to there. So we use a different tangent line. We're going to use the slope of the curve at 2.5. Now, we don't know what the coordinates of the exact point are at 2.5, but we know the slope because we have the differential equation, right? So what we're basically doing is using a different tangent line now. And the tangent line would be tangent to the curve at this point, but we don't know that point, so we use this point instead. So we're going to be a little bit off. And the more steps you use, the further away you'll get from the curve, right? If you wanted to go out like to 4, it's going to get further and further away, right? But as long as it keeps curving upwards, if you use more steps, it'll be more accurate, right? What if I used 4 steps instead? So if we get rid of this, so what if you went every quarter? So use this tangent line for a little bit, then you use a new tangent line for a little bit, then a new tangent line for a little bit. And what happens is you kind of follow the curve. It's not exactly on the curve, but it's close. And how can you get better? Well, use more steps. The more steps you use, the shorter you're using a tangent line. So you're going to be closer to the curve, right? And every time you use the new derivative at your new point, and so that's going to curve your little lines up a little bit more. Okay, so this is the general idea. So one more picture I'm going to draw here. So if we imagine how we can find these differences, okay? So this is your starting x point. I'm going to call it x0. Then you're going to go towards x1 right here. And the difference between those we call delta x. Okay, and delta x is some known value. If you're going from 2 to 3 using 4 steps, delta x will be equal to 0.25, right? Because you're going from going 1 using 4 steps, so you're going 0.25, 0.25, 0.25, 0.25. And then what you want to know is how much does the y change. So we have y initial, and we want to know how much does the y change. So if we use a tangent line, okay, we're kind of creating this triangle right here. right? So delta x is the bottom of this triangle. I want to know what is delta y. Now, it's not the actual value, right? The actual value is up here on the curve, but I can do this by using the slope of that tangent line, right? The slope is the change in y over the change in x, and the slope of that line is just equal to the derivative at the x0 point right here, right? Because we're using a tangent line. So this is f prime of x0, which we can get because we have the derivative. We know what the slope is, right? So if I want to know delta y, I just multiply by delta x. It's going to be the slope times delta x. Then what we do is we just restart with that new point. So this new point is going to be x0 plus delta x and y0 plus delta y. We use that and we do the whole thing over again. Now we use the slope at x1, right? So this term's kind of complicated, but when you actually do this, this is not hard at all. So let's do it with an example here. So we have a differential equation, x plus y. This looks kind of like the ones that we did the slope field with before, right? This would have a really hard solution, but it's very easy to linearize. Very easy to make a slope field too, right? So what we're going to do is we have our starting point. So they tell us 1, -1 is on the particular solution f of x. They want us to use 4 steps to approximate f of 3. So let's kind of draw what's going on. I don't know what the curve looks like, but they tell us 1, -1 is on the curve. Let's say the curve is like increasing concave down. I don't know if it is or not, but maybe it is. They want us to find f of 3. Here's 3. They want us to approximate that using 4 steps. So if we're going a total distance of 2x units, we use 4 steps, then our delta x is going to be 0.5. So we move 0.5 every time. So 0.5, 0.5, 0.5, 0.5. And what we want to do is we want to figure out what approximation we have for f of 3 when we use tangent line, tangent line, tangent line, tangent line. Okay. So what I always do here, I always write the same thing out. I write start. And then we have, let's see here. So our starting point in this case is going to be 1, -1. And then what I have next is I'm going to have the derivative of that x value. So I usually call this m, because that's going to be my slope. So really what this is going to be f prime of whatever that x value is. So I write x0 because that's the starting x value. And that's going to change every time because I'm going to have different x value as we go. Okay, then after that, I'm going to write my delta x, and delta x is never going to change. So in this case, delta x in this case is always going to be 0.5. So it's going to be 0.5 every time. And then we have the delta y, which is just m times delta x, right? We showed that on the last one. It's just the slope times the change in x is going to tell us how much we change for the y value. And then we're going to have our new point. So our new point is going to be x plus delta x and y plus delta y. That's how much the x changed and how much the y changed. So let's see if we can do it. So here we have our starting point, 1, -1, and I really shouldn't, I guess, put f prime of x0 here because this differential equation involves x and y. So you could write dy dx here, right? This is dy dx because it's the slope, it's the derivative, slope of the tangent line. Okay, so the slope at this point is going to be x plus y. That's 0. Well, that's easy. Delta x is 0.5. So it looks like we're at a max or a minimum point here maybe because the slope is nothing. Now delta y is m times delta x. Well, that's 0. Now we have our new point, x plus delta x, that's going to be 1.5. And we have our y plus delta y, which is still -1. And that's our new starting point. So now we have 1.5, -1. So the y didn't change at all because we had a max or minimum. So we said, well, if you use the tangent line, then the y isn't going to change. The x moves on, but the y hasn't changed at all. Now we're going to use whatever the slope is at the next point. So the slope this time, if we add them together, is 0.5. Change in x is still 0.5. Change in y is the slope times the change in x, which is 0.25. So now we have our x plus delta x. So that's going to be 2, and our y plus delta y. So -1 plus 0.25 is -0.75. So you must be increasing, right? My pictures are bad because I have no idea what this looks like, but it doesn't matter. All right, so our new point is 2, -0.75. So our slope there is x plus y. That's gotten from the differential equation. So 2 minus 0.75 is 1.25. Change in x is 0.5. All right. Now, you might have to get a calculator for this at some point, but usually what AP does is they only have you go until you have to make like one sort of difficult calculation. So half of 1.25, that's not actually too bad, right? That would be 0.5 plus 0.125. Let's see, that would be I got to think about it. 0.5 plus 0.125. So that's going to be 0.625. Okay. So let's see if I can still do this without having to go to a calculator. My pride might be my downfall here. Let's see. So now we're going to have 2.5 for x, right? We just march on 0.5 every time. Now the y is going to be negative 0.75 plus 0.625. Let's see, those differ by 0.125. I think it's going to be positive point one. Nope. Nope. I'm going to do it. I'm going to go to the calculator. Let's see. Keep them. Here we are. We got it right here, ready to go. So let's see. What do I have to do? We had to do, so let's make sure that's right first. 1.25 times 0.5. I don't trust myself. 1.25 times 0.5. That does give us 0.625. Excellent. And then I want to do that minus 0.75. 0.75. Negative 0.125. I was kind of on the right track. So this is negative. We get the right color here. Negative 0.125. Of course, I got the wrong color. All right. So that's our new starting point. 2.5, negative 0.125. Maybe we should have done this in fractions. These are all nice fractions. That's like 3/4. This is 1/8. Anyway, we'll keep going with decimals because that's where we are. And usually you see AP do this with decimals. So our slope now is going to be multiplication of those two. So I'm glad that I went over to the calculator for this. Times negative 0.125. So 2.5 times negative 0.125 gives us negative 0.3125. Negative 0.3125. Delta x is still 0.5. Oh, I did that wrong. Sorry. Messing up all over the place here. We just add them together. We add them together to get this, right? So 2.5 minus 0.125 is going to be 2.125. So now we multiply, right? Half of 2.125. I'm going to go for that. Half of 0.5 times 2.125. That gives us 1.0625. This is getting old. 1.0625. And now we're going to add that to our y value. So if you add 1/8, and I think that's like a 16th. So we do 1.0625. We're going to add to that. What was it? Negative 0.125. Negative 0.125. Gives us 0.9375. So we have 3.9375. Whew. Had to work hard for that. I hope I wrote it down right. Yes, 0.9375. Awesome. Kind of clunky with the touchscreen here. But anyway, so now we stop, right? Because we have f of 3. So f of 3 is approximately 0.9375. 9375, if I could write. Whew. Gosh. Okay, bit of a pain with the decimals, but if you have a calculator, it's not too bad, right? So the point is, we keep going by halves with the x, and the y is increasing based on the slope, whatever the slope is for different values, right? So we use the slope using the derivative, right? We just add the two values to find what the slope is, and then we multiply by the change in x, which doesn't change, right? It's always 0.5 every time, and that gives us the change in y, and then we add it to the original y, and then we get our new starting point. Okay, got a rainbow of colors at the end there too. What a deal. All right, why don't you guys try this? See if you can figure this out. And then we'll try it together. One thing to notice here is we're starting at 2, 3. We're ending at 1.5 using 5 steps. So we're actually going backwards. So think about what that delta x is going to be. See if you can give this a shot, give it a shot, and then we'll come back and try it together. All right, let's do it. So we got our start. We got our slope, right, which in this case is going to be 2x minus y. Got our delta x, and then we got our delta y, which is m times delta x. And then we have our new point. So we're going to start with the point 2, 3. The slope in this case is 2 times 2 is 4 minus 3 is 1. Change in x here is going to be negative 0.1 every time, right? Because we're going from 2 back to 1.5, so we have to have negative 0.1 every time. And it'll still work, right? All that's going on is we're just going backwards. So we're using the slopes like going backwards on the curve, kind of like this. Okay. All right. So the slope is, the change in y is m times delta x, which is going to be negative 0.1. So our new is going to be 1.9, and then 1 minus 0.1 is going to be, no, sorry, 3 minus 0.1 is 2.9. I'm going to use my calculator on the side here so that I don't have to worry about going back and forth to the calculator again. All right. So next up, so that's our new starting point. So we got 1.9, 2.9. So 2x minus y is going to be 2 times 1.9. It's 3.8 minus 2.9. Minus 2.9, that is 1.9. Okay, delta x is negative 0.1 again. So our delta y, if we multiply those together, it's going to slide this over and make it negative. So we got negative 0.19. All right, so our new place is going to be 1.8 because we drop 1.1 from the x again. And then 2.9 minus 0.19. See if I can figure that out. So we do 2.9 minus 0.19. Gives me 2.71. Okay. All right, so that's our new starting point. We got 1.8, 2.71. So now we do 2x minus y. So 2 times 1.8. 2 times 1.8 minus y is 2.71. I get 0.89. Change in x is still negative 0.1. Multiply them together should be negative 0.089. So we take that away, so we have 1.7 now, and I'm going to do 2.71 minus 0.089. Gives us 2.2621, excuse me. All right, that's our new starting point now. We got 2 more steps to go. So 1.7, 2.621. So 2 times 1.7, 2 times 1.7 minus 2.621 gives us 0.779. Fun numbers on this one. All right, negative 0.1 for our step again. So if you multiply them together, it's going to be us negative 0.0779. So we have 1.6, and then if we do 2.621 minus 0.0779 gives us 2.5431. Okay, one more. So we got 1.6, 2.5431. And then our slope is going to be 2 times 1.6. And then minus 2.5431 is 0.6569. All right, delta x is still negative 0.1, so this is going to be negative 0.06569. And our new point is going to be 1.5. Finally, we got there. And then we have 2.5431. Just do this on my calculator, minus 0.06569. Gives us 2.47741. Remember, you need 3 decimal places, but this is exact. So that is our approximation for f of 1.5. Approximately equal to 2.47741. Now, there we go. Sometimes they'll ask if it's an over or underestimate. So to check if it's an over or underestimate, it has to do with concavity, right? Same with linearization. If you have a concave up curve, linearization is an underestimate, right? Because the point on the linearization is going to be lower than the point on the curve. Same with Euler's method. If you know that a curve is concave up the entire time, it's going to be an underestimate because it's going to try to keep up with the curve, but it won't make it. If it's concave down, it's going to be on top of the graph. It's going to try to stay down with the graph, but it's not going to be there because you're going to be too high every time with that linearization. That's only if it's the entire time. So they tell you like the second derivative is always positive. You know the graph's concave up. Again, just draw a picture. Draw a picture, draw in some tangent lines and say, oh, it's too low or oh, it's too high. All right, so Euler's method. Just 2 examples. Took a little bit of time, but not that bad as long as you set up this chart every time. Love you guys. That's why I'm here. Have a great day. I'll see you in the next video.